Today we shall be learning about the Amperes law. This is also a method to find out the magnetic field in certain situations. So the law states like that. The line integral of magnetic field B over a closed loop is equal to mu 0 times the total current crossing the open surface. Now, so that means it says that integral of B dot dl over this closed loop, this means is equal to mu 0 into I. What is I? I is the total current crossing the open surface. Now, for simplicity, we will take this that. So for simplicity, we can take a piece of cloth or a piece of paper like this. See, this paper itself is an open surface. So I take this one. See, this paper itself is an open surface and its boundary is known as a closed loop. Boundary of this paper is a closed loop. Okay, so what we'll do here is that, say, of the shape of this paper, we have a closed loop like this. And suppose a current crossing the paper like this. This is I1 and say this is I2, say this is I3, and sorry, this is say I4, and we are calculating the integral of the magnetic field over this closed loop. Okay, suppose this currents dominates, this I1 and I4 dominate over this. So the net current is flowing out of the thin of the paper. So if you choose this DL like this, DL, right, this whole loop is divided into this small length DL on the circumference, right? Got it, na? Like this. And suppose this B magnetic field at this location happens to be B. Okay. So integral B dot dl here. So integral of B dot dl is equal to, in this case, mu 0 into, I will write here, I1 plus I4 minus I2 minus I3. Why this sign convention I have chosen is that, suppose we know the right hand thumb rule that if there is a current flowing this way, then the magnetic fields will circulate like this. And if there is a current flowing this way, then the magnetic fields will circulate like this. Now, we have chosen DL this way. So, that means the circulation we have chosen in the anti-clockwise direction. See, DL choosing this way. So, I would like to add it this DL1, DL2, DL3, DL4 like this. So, that circulation I would like to perform in the anti-clockwise direction. So, this is the direction of circulation. So this current you have to take positive, flowing out of the plane of the, I mean through here, through this closed region, right? Okay, now remember that this field B is the field due to currents inside and maybe outside also the loop. But as we have seen in Gauss's law, right, the field here, the electric field E, depends on the charges. See, it is due to the combined effect of the charges within the Gaussian surface and outside the Gaussian surface also. So there may be current carrying wires outside the loop like this, say 1 2 3 4, say I5, say I6 and I7, like that, but these all won't come in this equation, right? This is what Ampere's law is all about. So integral B dot dl, see this B magnetic field here is due to the combined effect of all currents inside and outside, but the result shows is equal to the integral of B over this closed loop is equal to mu0 times, it depends on the current inside the loop going through this open surface. Okay. Now this is the open surface we have chosen. Now see, the open surface and the closed loop are very general things. Okay, now say I bring in this one, say I bring in this packet, right? This is a packet, or say I will make one. Yeah, just a minute. Now the open surface is a very general thing. It may be like this also. See, this is a cone, right? So this means an open surface, and this is the associated closed loop. That the thing I mean that for open surface, the surface need not be flat always. The surface may be like this also, maybe like a cone or a bag you carry in the market. Right? Suppose this is a bag, there lies this vegetables and all those things. So this whole thing is the open surface, right? Open surface, and its circumference is the closed loop. This is it. This is the closed loop, the circumference of this open surface. So it may happen that, so you are calculating this B dot dl in this direction. Say this B happens to be here, B dot dl, and there is current flowing through this open surface in this way. This is the current carrying wire. It pierces this open surface and goes straight through here. Right. So for this also, see, this is equivalent to, if I draw it this way, this is the circumference or the loop B dot dl. B is somewhere here, and for this, the open surface, this is the current crossing the open surface I. So for this I can write integral of B dot dl equal to mu0 into, here it's I only. So remember that the open surface always need not be a flat surface. It may be a curved surface like this also. However, in most of the problems we solve, a flat surface will be good enough for our problem solving purpose. Okay. So this is the Amperes Circuital Law, or Amperes Law. Integral of B dot dl is equal to mu0 into I. And remember that if you take dl this way, then this is the direction of I, and if you take dl this way, then you should take this the direction of I. Okay. Now a few applications. Okay, and remember that mu0 is the permeability of free space. Okay, but see, Ampere's law is true. See, you will apply the same Ampere's law in vacuum and in a magnetic substance also. In both cases it is the same law. Remember, in Gauss's law also, in vacuum Gauss's law, and in a substance or a dielectric Gauss's law is the same. So you had this same constant. So integral of E dot dA is equal to Q by epsilon naught. This was Gauss's law, and Gauss's law does not depend on medium. You have this same epsilon naught here for vacuum, and for dielectric also what changes is the charge. Similarly, in magnetic substance, you will see this epsilon naught doesn't change. What changes is the current. In magnetic substance, you will see the atomic currents flowing, or you will realize, rather not see, the atomic current flowing in the loops. However, that we will deal in a later chapter. Okay, so let's deal with applications of Ampere's law. Okay, first one is to find magnetic field at a distance r, from a straight infinite wire, carrying current I. So this is the straight infinite wire. So at a certain distance r, you have to find magnetic field. So here we will apply Ampere's law, but before applying Ampere's law, you have to have some knowledge that regarding the direction of the field and symmetry and all those things. So here you know that this magnetic field forms these circular loops, and that too it is symmetric. So we will take this as the Amperial loop, and this is the surface, right? So this, you know, this is the magnetic field is same throughout, and you take this as the Amperian the open surface, flat surface, and this is the loop. So if you look from the top view of this thing will be like this. So this is the direction of the field. Absolutely, there will be no bias, right? And this right through the center, and this is the closed this is the open surface rather, and this is the closed loop. This circle is a closed loop, the circumference of this open surface. Okay, now obviously dl is in the same direction, right? Dl is this way. So dl's, little dl's. Okay, so integral b dot dl, what will you get? Closed integral of b dot dl is equal to b multiplied by, see, b is constant, na? Dot dl, b dl into cos of 0. So integral of dl, sum of all this length is 2 pi r. So this has radius r. Okay, so this is equal to mu 0 into current crossing this loop, I. So therefore you get b equal to mu 0 I by 2 pi r. So pretty simple, we have reached at this result with ease. And earlier we have used what? We have used integration earlier. Here just straightforward, we apply Ampere's law and calculate the field. But these all will hold true in case of symmetrical circumstances, obviously, not in all cases. If you have a finite wire, obviously finite current carrying wires don't exist, they form a closed loop. Say if you have to find magnetic field due to a finite part of a current carrying wire, let this be a large wire or infinite wire. Due to this finite part of the wire, if you have to calculate magnetic field here with Ampere's law, you can't do that, right? Okay, now next thing is the long solenoid field inside a long solenoid. Here n is number of turns per unit length. And I is the current. So it's like this long solenoid, and current flowing like this. So this is the magnetic field B inside and on the axis of the solenoid. Now what we'll do is that, so say over a large region or over a substantial region, the field you can assume it to be constant, and I can have an Amperian loop like this rectangle. Did you get this point, or I'll try to convince you by a 3D diagram. I'll try my best. See. This is what I have drawn is a solenoid, right? I have tried to draw the solenoid. I have tried my best to draw a solenoid. I don't know whether it looks like a solenoid or not. See. Now, this is the loop, Amperian loop. There it is. And this is how the coils cut the loop. It's like the spiral binding on your book. If you try to visualize that, it is like the spiral binding on your book. Now this part is visible, right? This is part. Okay, so now this is the thing. It like a spiral binding, and say this length happens to be x. This length happens to be x, and there, let me draw the magnetic field here. This is the magnetic field B. It's on the axis only, it's not outside, right? There it is, magnetic field. Now this magnetic field is B. now, and the current, this is the direction of magnetic field, and the current crosses the loop like this. I hope it's not that bad, right? Let me draw a top view. Yeah, this is the top view, and this is X, this is X, and these are the currents. Dot for this all. And this is the direction of the magnetic field here. Almost you can take it as constant because it's a long solenoid, and in a substantial region inside it you can treat it constant. So that's B, and let's make a little dl. There it is, little dl here, right? So no fields here. So we will apply Amperes law here. Integral of B dot dl is mu 0 into I, right? So integral B dot dl is actually B into, sorry, that's not dx, it's x. Please correct it, right? X. See, x, this is x. So B multiplied by x equal to mu 0 into I. What is the total current? In unit length, number of turns is n, small n. So in x length, number of turns is n into x multiplied by current in the loop. Current in each turn rather. So this is the total current crossing the loop. So therefore you get B equal to mu 0 Ni, and we have got the same result before also by integration. Well, you can't apply this Amperes law for a finite solenoid. I mean a solenoid of finite length you can't apply, right? See, Amperes law will be true, but it won't help you in calculating the field, right? So for applying this Amperes law for a substantial length x, you have to have this field constant. And see, it's so long solenoid that there is no field outside. What happens actually after some time, it will loop around, right? What happens? A solenoid is no different than a magnetic needle or a bar magnet. So what happens here, that if we have field here inside the solenoid, so the field will loop back like this, right? Fields will loop back into this like this. It will form closed loops. But in our case, what happens, that it's a long solenoid, right? So it was a long solenoid, so the looping back happens after sufficient time. See, this was the case. Our case, it was a long solenoid, and we were working with this rectangle here. So this looping back is much far away. So we don't have to worry about this. There is no field absolutely here. There is field only on the axis. It was application number 2, right? Solenoid. Now this application number 3 will be a toroid. Toroid is it's like a solenoid itself, right? It's like this, it's a solenoid, it's bent like a circle. That's a toroid. Just let me draw the diagram, it will be more clear. Yeah, like this. However, that's a toroid, and this is the radius of the toroid, radius r, and I is the current in a turn, and this capital N is total number of turns. Total number of turns. See, now here what happens, what will be the direction of the field? See, depending on the direction of current, suppose the direction of the field is this way, it will form line as a closed line like this. So this is the direction of the field B. So here we have to choose the closed surface. So we can choose this circle of radius r as a closed surface. Here this is itself our closed surface, circle of radius r, and you have this magnetic fields B on its circumference. And as you see in this diagram, see here, these currents will cross this surface, right? The currents will pierce through this surface here. Okay, so that's dot actually, right? See, we have chosen this B here, so the current is coming out of the plane of the paper. If current were this cross, then we have to consider this B this way. Okay, so little dl is here, B and little dl. So see, B dot dl is actually B dl into cos of 0, so B into dl only. So integration of B dot dl is B into 2 pi r. Summation of this dls will be 2 pi r circumference, equal to mu 0 into, see, what is the total number of that total current crossing the loop. Through each turn it is I, and multiplied by number of turns n. So therefore you get here B equal to mu 0 Ni divided by 2 pi r. So isn't it same as the solenoid? See, here if you divide n by 2 pi r, so you get this small n, number of turns per unit length. So it happens to be the same thing. Now, next question number 4. There will be a current carrying plate, right? No, just wait. A large metal sheet, a large metal sheet carries surface current or carries surface current surface current of k amperes per unit width. The thing will be clear in the diagram. I will show it. Find magnetic field near it at points P and Q. See, this is the infinite metal sheet and it carries current this way. So here is P and Q. Did you get the thing? Did you follow the thing? Where the current is flowing? If a slight difficulty in following, I'll try to draw a 3D diagram of the same. So this is a metal sheet rather. I am showing a part of this metal sheet, right? It's a large sheet. I am showing only a part, say this cut part of this metal sheet. Right. Now here current flows in these directions. Okay, so this is the width actually. Suppose this width happens to be looks like width. Suppose this width happens to be B. So through this section, so I'm interested about this current. So this much through this width, the current is equal to how much? See, per unit width it's K, so it's K multiplied by B, right? Through this portion only, right? Current through this section only is K, current per unit width multiplied by the width itself. I think it's now clear, right? What this diagram we have shown, we are looking from the front, right? That's a front view. Current will appear like dot. This is point P and this is point Q. You have to make so many diagrams for each problem. Okay. So at P and Q, let's see the direction of the field at P and Q. It is infinite sheet. Okay. Now, so this is point P. Place it here. Point P. Now, due to a current carrying wire here, what is the direction of field? Solely due to this wire, you have field like this circles, and this is the direction of field, right? And you have a similar current carrying wire here. Due to this current carrying wire, direction of the field is this way. So what is the resultant field? Resultant field is this way. So from symmetry we can see that if you divide the right side of P and the left side of P, the space, into two halves, then if there is a current carrying wire here which produces a field at P, it's like this, right? If it is this, a similar counterpart you have here. So due to this, the field at P will be this way. So resultant field here is this way, and so in the top part, this is the direction of the magnetic field. On the bottom part, this is the direction of the magnetic field, and these two are equal, obviously. This is B and this is B. So we'll take an Amperian loop like this. Again a rectangle. In this diagram, what will be the Amperian loop? Like this, right? Okay, and we take this as X. Suppose you take this as X. This is Amperian here. So this length I take it as X. So field is throughout in this direction. This is the direction of DL. Little DL comes here. See, B dot DL here, and here it is 0, obviously, because field is perpendicular to DL. So here B dot DL becomes B into X, and here it is 0. So here again it is B into X, and here again it is 0. So that's integral of B dot DL over the closed loop is equal to mu 0 into, see, the width is X, so the total current is K into X. So therefore B equal to mu naught K by 2.